layer of bosons in the sky.
There's a layer of bosons in
It's
this.
called the boson layer. Thanks so much. Sorry, friends. Okay, sorry.
Famously remarked that now the rest is chemistry.
So, yeah. It should
I mean, if you are only as smart as Newton was, let's say, you're smarter than Newton, but physicists are arrogant, and secondly, because they keep repeating the same old jokes. So
It's true.
Hello and welcome to part 2 of this episode of Friendship with Science. I don't know why it's not a different episode. You could have made it a different episode also, but it's part 2 of the particle physics episode. Shashi, please introduce where we were and what is going to happen now.
So last time we ended off with the uncertainty discussion of the uncertainty principle. So now we will take up with Sridhar the beginnings and the depths of quantum mechanics and lead all the way up to the standard model. That's roughly the journey that we're going to go through right now.
Okay, so this uncertainty principle, sorry, I have again very dumb question. Is it a problem of measurement or is this a property of the universe?
that's hardly a dumb question. No, it's not a problem of, it's not a limitation of our measuring processes, but it's a fundamental property of the universe itself. So fundamental property of this quantum world. So where it becomes relevant is where the scales are small enough for it to be relevant. And so that's the point. I said, like, we were talking of 100 millionth of a centimeter. So our understanding would be that if we keep going smaller and smaller, naively we would think that if Newton's laws work so well in the macroscopic domain, then why should it not work in the microscopic domain? I didn't mention electromagnetism and Maxwell and so on, but that is also part of this, what is called classical theory. And so one would have expected that even, suddenly you go down to 100 millionth of a centimeter and the same laws should hold. Laws should be universal. But it turns out that at that level, matter gets to become subtle in a way. And this solidity that we attach to matter at our familiar scales, that solidity starts becoming a bit fuzzy. And so it's now replaced by quantum mechanics, so Newton's. And that transition point, where does quantum mechanics start? Where does Newton's law's validity end? That is certainly not known. In fact, it's one of the hotly researched problems today. Even after 100 years of quantum mechanics being very, very good at doing all the calculations that we can do with quantum mechanics. This part of it, how it corresponds with our, so this connection between the microscopic and the macroscopic world, that is not yet clear to us. But all we know is that there is a certain stage, like say at the scale of the atom, certainly Newton's laws don't work, certainly quantum mechanics takes over. And in that world, the uncertainty principle is a fundamental feature of that universe. Yeah.
Sorry not to cut you off. Okay, so I don't know how to even ask. This momentum and position cannot be known at the same time. We're writing this in passive voice. Known to who? Like, if I am let's say I am the neutron or the proton in the atom, relative to me, is there any way, like the position of the electron can be known. I'm saying from an outside observer, it might be true that you can never know for whatever reason this thing. Or for even the electron itself, can it know its own momentum and this thing at the same time?
Yeah.
Sorry, I don't know what I'm asking.
No.
Very interesting question.
What one is saying here, known is basically, you see, we need these 2 bits of information. As I said, even when we were talking about Newton's mechanics, to be able to solve what is called an equation of motion, we need this at one given time. We need to know the position, we need to know the momentum. Okay, this was what was told to us, right, at that time. That give me the force, give me the position and momentum at one point of time, and I'll give you the entire trajectory. This was Newton's claim. Now, what Heisenberg is telling you is that you still know the force. So, in that sense, quantum mechanics is still mechanics. It's not, some people claim, oh, quantum mechanics is not mechanics. That's not true. It's still mechanics. By mechanics, I mean that if you give me the position momentum at this point, I know the position momentum at the immediate point, at the point neighboring to it. And I go in small steps and construct the whole trajectory. That's the idea of mechanics. And quantum mechanics is still like that. Okay? But what is not known is the position momentum at that one point initially. So you, with that blur, you can actually map the trajectory, but you cannot map the trajectory, sharply as you did in classical mechanics.
Got it.
Okay.
Got it. So
known is really about a question about the ability to actually solve that equation.
Got it. Got it. Got it. So instead of being like a very pinpointed particle, it might be a probability function.
It is a probability.
It is a probability function. Okay. So maybe okay. Got it. So it's like beyond our understanding.
Not beyond our understanding, but that is what we understand.
Beyond Newtonian understanding. Maybe. No? Okay. Anyways.
Yeah.
No, so the thing is, at the
use the word
quantum level,
beyond.
this is useless information.
Yeah, exactly.
I mean, in the sense, what the quantum world is saying is that ask me the right questions.
Yeah.
You're asking me Newtonian questions, position, moment. Ask me the right questions. So if you ask questions about the wave function, then the quantum world reveals itself to us.
Right.
So whatever we want to measure and know about atoms and to the accuracy that we want to know it, we can, as long as we design experiments where, so in a sense, we can say these position momentum are complementary variables. So if we design experiments where we are not trying to measure a set of complementary variables of that kind, we can always do it with whatever precision we like. And if we are measuring such complementary variables, we know what is the uncertainty within which we can measure it.
Sorry.
We're just asking, just to sharpen that for you a little bit, it's that you're asking for a different set of things.
Yes.
Yeah? And
got it. Okay, sorry. Again, I'm not done. Like we're talking about emergence phenomenon. Could we look at this as like a certain amount of atoms then becomes a molecule which behaves in a particular way? Is like a certain amount of wave or energy when it's together, it starts behaving like a particle. Is this like an emergence thing? It's not
really.
Completely.
These are two complementary ways of looking at the same reality, same electron. But and I wanted to emphasize that these are two models that we use, conceptual models that we use, which we are trained in and we use it. And those models are used, one or the other, if you use them by their own, those are limited in understanding the quantum world. But if you now bring in quantum mechanics, it kind of combines both these models in some more fundamental framework.
So if we
terms of this probability function that you were talking about.
So basically, if we know only two colors, red and blue, then we look at purple and say it is a duality color. But instead we could just call it purple. Is it like that? Like one thing could be wave and the particle at the same time. It's just that our understanding was rudimentary before this. Sorry, I think I'm asking very stupid.
No,
it's not stupid at all, because I think it sort of is pushing our boundaries also of what we mean by this understanding.
No, it's
Sorry,
not.
it's
But
not-
sorry,
you know.
to interrupt, but it's not just a mixture of wave
Yeah,
and particle.
exactly.
A
Okay.
purple would be just a mixture of red and blue. This is not just a mixture of wave and particle.
Exactly.
That's why I use the word transcendent, even though it's a dirty word, because it's misused so badly in other places. But by transcendent, I mean something which is not in this plane. That these two concepts occupy a plane. So wave, particle. The wave is this, particle is that. And by mixing, you will be still on the same plane. But by going to another level, a transcendent level, you're not on this conceptual plane, you're on another conceptual plane. And that is really the wave function of quantum mechanics. It's something else which we can try in limited circumstances to understand as a particle or a wave. But it is something which we now only know in terms of a mathematical function.
Got it.
I guess these particle and wave pictures also are used from our everyday experience of the things, right? And we are trying to extrapolate those pictures into this realm. But what Sridhar is saying is that the picture is completely different altogether, right? And that picture may be viewed sometimes as a particle, sometimes as a wave, but it's neither.
Got it.
Right?
Got it.
And a lot of those confusions and paradoxes you tie yourself into when you try to do this, when you try to resolve it in terms of this or that, because it's something else that we are talking about.
Got it. Got it.
Yeah.
Okay.
So Sridhar, I mean, we're talking now about this period in science where not only these ideas of quantum mechanics are in the boil, but there's this other big revolution that's going on.
Yes.
Relativity.
Yes.
Yeah, are these related, or these are two separate things, or?
Yeah, they are two separate things to begin with. I mean, I was actually in this narrative, I was trying to see where to bring in relativity, because also as we proceed, that is also important to what I'm saying. So relativity, Einstein's name is largely associated with relativity, but there were others who contributed to it. And basically, I need to go back just a little bit to do this, and that will help me cover some bit of electromagnetism that I skipped. Okay, so magnetism is a phenomenon that has been known for many centuries. Okay, probably thousands of years, and magnetism. So, in fact, the Vaisheshika philosophers, they talked of magnetism as one of the examples. Quite interesting. But electricity was, being seen in different contexts, static electricity and so on. But eventually, a proper theory of electricity and magnetism evolved in the middle of the 19th century. Okay. Before the theory involved, there were a lot of facts about electricity, because electricity was then being experimented with and people were understanding more and more about this phenomenon. But what was interesting is, from a lot of experimental facts, thanks to people like Faraday and Ampere and people like that, the new realization that came about was that electricity and magnetism, even though they look like completely different things, they are one and the same thing. Okay? And one of the things was that if you have two parallel wires and you have currents going through them, and if these currents are not constant in time but are changing in time, then these wires attract each other. So there's a magnetism which is created by the time variation of electricity. Similarly, we know in a cycle dynamo, that you have just two magnets and a coil, and you cycle and this magnets whirl around inside. And just their whirling around creates a time-varying magnetic field, and that induces a current in the coil. So the faster you cycle, the brighter the lamp and so on. Yeah. So the time variation of electricity gives rise to magnetism. The time variation of magnetic field gives rise to electric field. Maxwell, James Clerk Maxwell, this great Scottish physicist, asked this very interesting question. He put all this together, he formulated the mathematical theory of it. But essentially, the question that he asked, and I'm simplifying it really, is that if the time variation of one supports the other, what if you have both of them time varying? Okay. And the answer then is that the time variation of the electric field will sustain the magnetic field, and the time variation of the magnetic field will sustain the electric field. So they can sustain each other and can become independent of any medium, independent of a conductor or independent of a magnet, and can radiate as radiation and go through space. Okay. And he churned these equations, wrote down showed that you actually get what is called a wave equation in mathematics. And he found the velocity of that wave and turned out to be exactly the speed of light.
Wow.
Okay. So he said, so in one fell swoop, he had not only unified two very distinct, disparate theories, electricity and magnetism, but he actually brought in the bonus of light, theory of light and optics also as an extra thing, buy two, get one free kind of thing.
Wow.
So electromagnetic radiation, he then showed, so what we understand as light, if we now understand this as electromagnetic radiation, and as you correctly said, part of it is the visible spectrum from red to violet, but above violet and below red, we call it infrared and ultraviolet, there's still electromagnetic radiation beyond the optical spectrum, right? All that is fine. But if electromagnetic radiation is a wave, what is a wave? Wave, I said, is, like you take a string, shake it, and that is a wave. So in order to have that wave, I need some material, like here the string, or waves on the surface of a pond. I need some material medium in which this disturbance can propagate, because the wave is a disturbance. So what is the material medium in which light propagates? That was the question. But light comes to us from the sun. Our atmosphere is reaching only up to here. Beyond that, there is no material medium. So the question was, what is the material medium then? And so this material medium got to be called ether. Ether was a old word from old ancient philosophy, which was the equivalent of akasha in Indian systems. And that was now being reused in physics. So the late 19th century, second half of 19th century, the search for an ether began. Okay. And these two very smart, one very smart American physicist who should definitely be called the father of American physics and not Millikan, called Michaelson. Michaelson and his collaborator Morley, they did this experiment to essentially measure the speed of light. Okay, so 2 or 3 facts, let me say it quickly. The light travels at finite speed, travels at an incredibly fast speed, but it is still finite, which is also quite mind-boggling because one, it travels at 3 lakh kilometers per second, okay? But it is not infinite, and that makes a huge difference. Okay? So because 3 lakh kilometers means light from you to me takes some time to reach, but that's so small we don't notice. We think this is instantaneous.
But the key is that it's not instantaneous.
Not instantaneous. So light from the moon takes 1 second. Light from the sun takes some 8-9 minutes, whatever. Okay? Light from distant stars take more and more time, and so on. So suddenly, this idea of
time
of everything existing in one time slice goes away, because when we're looking out in space, we are looking back in time. We're looking at a distant star, it's 500 years old. And even distant galaxy, then it's some thousands of years old, or millions of years old, or even more. Okay, so history and geography get mixed up in very interesting ways here. Anyway, so coming back to this electromagnetic radiation, time travels at a speed of 3 lakh kilometers. if I travel at speed of 100 kilometers in my car, and I travel in the direction of the beam of light, then it will become slower by 100 kilometers. That's obvious, right? If I got it?
It should not be. I know that it doesn't become.
No,
I've seen on a YouTube video.
Yeah, but you're too smart.
It should become.
I'm assuming you're not that smart.
So, it should.
If you are only as smart as Newton was, let's say, you're smarter than Newton, but
I've seen on a YouTube video exactly.
No. So what I meant, okay, to rephrase that, if I know my Newtonian mechanics,
yes,
and then if I am in a car and you're in your car,
I think that.
If I'm moving at 100 and you're moving at 120, then if you're moving in a direction opposite me, I'll see you as moving at 120. If you're moving in the same direction, I'll see you as moving at 20. This we all know, okay, relative speeds. So when we want to travel faster than speed of light, all you have to do is shine a beam of laser light from one direction and go opposite it, and you get the light to travel faster.
Okay.
No?
Got it.
3 lakh kilometers plus 100 kilometers faster.
Yeah.
But the funny thing, Michaelson and Morley in effect did this experiment, okay, measuring it in the direction and against the direction. And their results turned out that no matter how you move it, like what you're saying, light always travels at the same speed. So basically they said you have to give up all these notions of ether and all that, and really go back to our design table and design a new theory now. And that's what they did eventually. So basically this calculation that, adding and subtracting the speeds when you go opposite or that calculation cannot be right. That's what they said.
Got it.
So they, cutting a long story short again, Einstein came up with this. So actually a physicist called Lorentz cooked up a set of equations, which if you use those equations, then you actually satisfy this condition. You get the answer that no matter how you travel with respect to this beam of light, it will always travel at speed. But Einstein probed it further and moved it into a new conceptual framework, and that is called...
Was Lorentz also thinking about it in the context? He wasn't thinking about it.
He was thinking
in terms of
more classical terms. He was trying to keep all the Newtonian and Maxwell theories intact
together,
and then within that, try to cook up these equations. But that was not satisfactory. And Einstein realized that you have to actually go and throw away Newton's equation and come up with a new set of equations and accept this Lorentz transformations as the real one. And actually, nicely, they showed that if you're close to the speed of light, or if you're significantly close to the speed of light, then you see these effects. But if you go down in speed, if you have a very low speed, then you recover back all the Newtonian formula. So everything is good. So this theory of Einstein is called special relativity. And there's also a general theory of relativity which incorporates gravity and things like that. I'll not go so much into it now. Maybe in the end we can discuss this. But the special theory of relativity is a theory that we need to pay attention to whenever the objects that we are dealing with are moving at very, very high speeds.
Got it.
So just like if we go to small distances, we need quantum mechanics. If we go to high speeds, we need relativity theory. Okay. And
what if small objects start moving at the speed of light?
So then the question is, if small objects, like he's saying, move at very close to the speed of light, then what happens? What do we do? Then we have to actually synthesize relativity and quantum mechanics into a new theory, which is called quantum field theory. Okay. So, let me immediately tell you about a little bit about that. So that was the attempts people were making at that time to try to write down a generalization of quantum mechanics. So it turns out that if you are studying atomic physics or molecular physics, where you have to use quantum mechanics, the motion of the electrons on the speed of it is not that high. And so you can actually happily use non-relativistic, but quantum mechanics. So originally quantum mechanics was developed in that way. Now, people started worrying about this same question. What if you have both small speeds and small distances
Scales.
and small scales and high velocities, large velocities? And I can tell you, kind of, using an analogy of sorts, I'll try to tell you what it involves. Okay. Now, as I told you, there's an uncertainty principle of position and time, right? That if you get, so each of this, either position or momentum, you can measure only with some level of accuracy. That's what uncertainty principle is telling you. Because if you try to measure this too precisely, the other goes haywire. Okay. So there's a error on this and an error on that. There is a similar kind of uncertainty principle that comes with energy and time. Because you remember when I was talking about uncertainty principle, I used the word complementary variables. So position and momentum are complementary variables. Energy and time are complementary variables. So there's an energy-time uncertainty relation. And for that, I have this cute analogy. So imagine you're handling the finances in a company. Okay. So you're actually handling the cash. And you know that the accounts for that company are settled. I mean, they actually, check the balance and look at the credit and debit side and check the final thing only at the end of the week. Okay. So on Monday, you start fresh, and on Friday, before they go home, they check the accounts. In between, they don't check the accounts. So, but you are the guy who has all the cash in your hand. So you go there on Monday morning, you take away some cash from there, and you go and bet it on your horses. Again, you make a pile there, replace this money here, and take away the extra there. Okay. And in doing this, you have actually used the energy-time uncertainty principle, something like that, because you have a delta t, error in time, a week. If they were checking every moment, you would not be able to do this. But they gave you a interval in time. Interval in time. In that interval in time, you could actually manipulate delta cash. Okay.
This is actually the explanation to the Harshad Mehta scam, actually.
Yes.
Yeah, this is not even like
so quantum processes, this is what is happening. So they are stealing amounts of energy in periods of time that, so normally everything is conserved in even in these processes. That's a very beautiful thing. So for example, energy conservation still holds. Yeah. So if you look at the energy on, if you look at the energy on the credit side and the debit side, balance sheet has to tally. Okay. But you can do Harshad Mehta in the quantum world for precisely this reason, that you have a delta t here. And so you can violate energy consistent with that interval of time.
Wow.
Okay.
But this is a very beautiful analogy. It's a beautiful analogy that you're doing.
Yeah. Now, one more step. This Einstein's special theory of relativity, I forgot to mention, other than giving you these Lorentz transformations and saying that you have to do this kinematics or this speed calculation differently and so on. If you work out the consequences of this new theory of relativity, then it tells you that, so normally, again, in Newton's theory, energy is something which is basically just the square of the momentum divided by some 2m. Forget that. But if you have some momentum, then there is some energy. If you have no momentum, there is no energy. In Einstein's theory, it works out that along with contribution to energy coming from the momentum, there is a contribution to the energy coming from simply the mass of the particle. So even if the particle is at rest, it has an energy associated with it. Okay, and that is a famous equation, E equal to mc square, which everyone knows.
Yeah. Sorry, I'm just trying to understand again. Newton is saying that
E equal to p square over 2m.
yeah, like if something is moving, let's say, then it has energy that's moving,
Yeah.
right?
So in Newton's
Kinetic
theory,
energy.
Kinetic energy.
now
yeah.
forget potential energy. We are assuming there are no forces.
Yeah.
There is just a free particle.
Yeah.
So thing is moving, then it has energy. But if I just keep it, this is sitting at rest. It has no energy, no kinetic energy, right? In relativity, what Einstein is saying is even in the absence of forces or anything, and even in the absence of a potential, if this is at rest, it still has an energy related to its mass. So its mass multiplied by the square of the velocity of light, mc square, is the
So-called rest energy.
is called the
Got it. I don't know why I'm remembering. Maybe I saw it somewhere, but it's basically when you consider the photons. It's like if you consider the photons frame of reference, then it is at rest, but it still has energy.
Yeah, you can't go into the photon stream of
Okay,
reference.
so then I'm confused.
Because, yeah.
I'm confused.
Because you can't be at the speed of light.
Photon is
Yeah.
always
Right.
moving at the speed of light. If you are in the photon stream of reference, its speed has become zero, which cannot be. It always travels at the speed of
Okay,
light.
so you can't go to photon
Photon stream of reference.
Okay.
Yeah.
It's not allowed.
Equal to mc square. Okay. So, I mean, why I'm bringing E equal to mc square is because we just figured out that you can violate energy for some intervals of time.
Got it.
Okay. Now, that was coming from quantum mechanics. E equal to mc square is coming from relativity. Now, if I make a shadi of these two, then in that union, okay, I can now have this violation of, in this time interval, I can violate delta E amount of energy, and that delta E amount of energy can pop up as the mass of some particle. Okay, so out of nothing, just because of the uncertainty principle, you can create mass. Now, mass means what? You can produce an electron out of nowhere. Okay.
It's the opposite of an atom bomb.
Not
opposite
really.
of the atom?
As in atom bomb, I thought the mass is becoming energy.
Okay, yeah. So
I
to
see.
some sense.
Okay, I see what you're
Here you
saying.
Yeah,
like
in some
make
sense
yeah.
it is.
I
energy
see what
into
you're
matter.
Yeah. But
It's
it's just there,
yeah.
we're talking of one electron. Okay, and that electron is
Exactly.
produced out of this. But the point is, of course, electron has a mass ka to jugaad kar diya.
Yeah.
But if you have to be a consistent Harshad Mehta,
Yeah.
then you have to worry about the fact that the electron also has a charge,
Correct.
right?
Correct.
So that is in a different balance sheet. So
Yeah.
Harshad Mehta agar pakda jayega, unless he does some jugaad there also.
Yeah.
So you cannot just produce an electron, because you can't just create a negative charge. So then you say, create a negative charge and to also produce a positive charge along with it. Okay. So,
So this is coming
a sibling of the electron, which has the same mass as that of the electron, which behaves exactly the same as an electron, but has a positive charge.
Right.
Okay. This object is called an antiparticle. Okay, and it's a very spectacular prediction of the combined theory of relativity and quantum mechanics, what is called quantum field theory. So quantum field theory predicts the existence of these antiparticles. That antiparticles just exist, so that every particle that we know has an antiparticle. So you can have, for electrons, there are these particles called positrons, and so protons has an antiproton, so on and so forth.
So antiparticle does not have mass. It has negative mass.
No. It has the same mass as the electron.
Same mass, just
okay, but it's a different charge. Okay.
So in some ways, I guess the statement over here is that there are these two theories. There are those two pictures of the world. And by marrying these two and just doing big bookkeeping, right? You're marrying these two in some regime when the small meets the fast. And you just keep track of everything that needs to be kept track of. You cannot avoid the fact that something like this must exist.
Got it.
Okay.
So if that is true and this is true, then this
And
must
so
be
the guy
This must be
who
true.
first discovered that these antiparticles exist, he wrote down the equation and this antiparticles popped out.
Yeah.
This was one of the most brilliant theoretical physicists of the 20th century, a person called Paul Dirac.
Wow.
And outside the physics world, people talk of other people like Einstein or even Heisenberg or Bohr or whatever. But among physicists, Dirac is the big guru. Okay. So Dirac was the first person who wrote down this relativistic quantum equation called the Dirac equation. And he immediately saw that there are these positively charged particles popping out of his equation. And he was very embarrassed because he said the atom has only protons and electrons and neutrons also, which was discovered around the same time. So he said, what is this positive charge that is coming? So he tried desperately to say that this positive charge could be the proton. And but then he tried to save his face by doing that. But then a very smart physicist from Zurich called Wolfgang Pauli, who used to also be very nasty to people, he pointed out to Dirac that that cannot be a proton, because here this particle has to be the same mass as the electron. Your equations are showing that. Yeah. Okay. And the proton is 2000 times heavier than the electron. So it cannot be the proton.
Right.
So antiparticle is just a particle. It's just called antiparticle.
No, it is specific in the sense it's got the charge exactly opposite. So the important thing, okay, why you should look at, we were talking of atoms and so on. And one of the things I said about atoms is, like the Greeks and the ancient Indians said, that atoms are eternal. They cannot be destroyed. Okay? That shows up later in chemistry. One of Dalton's statements is that atoms can neither be created nor destroyed. Matter can neither be created nor destroyed. Okay, so the amount of matter always is the same. For the first time in the entire history of humankind, you bring a particle and an antiparticle together. This has positive charge, this has negative charge. You bring them together, whoosh, matter goes away completely. It's just energy. Okay. So it is possible. Annihilation. So just like you produced out of nothing, you can produce and you can dissolve them into nothing.
Then why is electron not called the antiparticle?
That's it's a nomenclature thing.
Got it.
Yeah. Also,
so
this
charge,
universe that we live in is somehow universe of electrons.
Yeah.
That ultimately is one of the big puzzles which is totally unresolved yet. About why do we live in a matter-dominated world? Why not in a particle world, not in an antiparticle world? Okay, that question we don't know the answer. Okay. But luckily for Dirac, what happened is just a year after he wrote down, and this hardly ever happens in physics. It takes a long time to verify things. But for him, luckily, in those days they were doing these experiments with, cloud chambers where they look for radiation. There's this cosmic radiation that was coming, which they look for that by putting a magnetic field in the experiment. And that's how, for example, electrons would be. So if you look for an electron in these cloud chamber experiments, it will show you a spiral, because in the magnetic field, this charged particle will spiral like this. And from the curvature of that spiral, what is the circumference of the outer spiral and all that, you can figure out the mass of this object. So and the charge also, it will go on to one side.
The ratio, the mass.
Yeah. So this guy actually found, this guy called Anderson, he did these experiments at that time and discovered in his tracks this electron coming like this and another spiral of the same curvature exactly, but in the opposite direction, which means it's the same mass because the curvature of the spiral is the same, but the charge is exactly opposite. So it's curving in the other side. So the positrons were discovered right away thankfully for Dirac. So the reason for bringing in this whole thing was to say that when you look at an atom, you say, this is it. You know, physicists were very, very proud of themselves. Chemistry guys are, you know, talking of 100 elements, but we are the real guys. You know, we have reduced those 100 to just 3. There's a nucleus with protons and neutrons, and there are electrons. That's it. The whole universe is made of just these 3 particles. Oh, what a beautiful theory. And it's held together by electromagnetic force. Okay? There's small gravitational force between the proton and the electron, but it is so small that it's irrelevant. So this is the entire, you know, you have given the answer for everything. But
so it did seem like a complete picture at that time even.
But already these antiparticles were discovered, then this picture seems already to be in trouble. But then just staring at this picture of the atom, which we are all familiar with, see that the nucleus is made up of protons and neutral particles called neutrons. So protons are all positively charged, neutrons are neutral, so this nucleus should just fly off. But it's held together in a very, very, very tiny region of space, as I told you, which is actually 100,000th of a atom is the size of the nucleus. So how are the protons and neutrons held so tightly there inside the nucleus? That was a big question. And it was in fact Heisenberg who first proposed this idea that actually that there is another reaction, another interaction other than electromagnetic interaction. So first of all, it doesn't care about the charge, the electromagnetic charge. It doesn't care about the fact that the neutron is neutral, the proton is positive and so on. And this interaction is also much, much stronger than the electromagnetic interaction. So it overcomes the electromagnetic repulsion of the protons and holds them together. And this was called the nuclear reaction or strong nuclear reaction because it is strong. It's actually about 100 times stronger than electromagnetic interaction. And so this already again complicates the picture. You have now a new interaction coming.
So Sridhar, I just want to make maybe a brief comment before we go into the...
Sure.
So this is a very interesting situation. And the timelines happen to be that, you know, like Sridhar said, let me just make one step back. So Dirac has married these 2 theories, like we were talking. And the consequence of marrying these 2 was this prediction. But remember, this is still in theory, right? It can be wrong. Yeah, it's beautiful or it's mathematically all correct and rigorous and all that. It can be wrong. So if that experimental observation was not made by Anderson in the cloud chamber experiments, that still remains an idea, right? But the fact that you've made the connection with an experiment suggests to you that, hey, I'm probably on the right track in marrying these 2. Right? And that's a very important point also in this dialogue between ideas or theory and experiment. In all of science, actually. You know, I can cook up...
In this entire development leading up to the standard model of particle physics, this has happened. It has been a constant, you know, interaction, very, very intense conversation between experiments and theory. So theory will come up with something, experiments will go and try to measure it and so on and so forth. So this has been the story of particle physics actually.
I mean, and although we say quantum field theory and so on, it's not just that, right? It's also the picture which is complemented by this experimental finding. So it's a picture of the world, not just a abstract idea. So I just wanted to make that comment about this dialogue, right, which has existed all along. Sometimes it's the experiment that leads the theory. So let's say this observation was made of these counter-rotating spirals before the marrying of these two. Then you would have to explain that fact. Right? Sorry, Sridhar. I mean, you were talking now about...
I was talking about how the simple picture of the atom now gets complicated. We now have antiparticles, and we also have strong nuclear interaction. So one new particle, one new interaction. So do you want to stop me here and ask something before I go ahead?
No, I think I'm pretty clear, actually.
Wow.
Weirdly, I'm actually.
All right. So there was another thing that was happening. People were noticing that some nuclei spontaneously were emitting charged particles. This phenomena were being observed for quite some time now. Slowly, nuclear.
By the way, what year are we in at this point?
Okay, Dirac's equation 1929, Anderson's
Still
measurement
black and
1931. The original setting up of quantum mechanics and the successful explanation of the hydrogen atom 1926, 27, around that time. So this is the...
It's been 100 years since that.
Exactly. I mean, and the relativity that...
relativity, Einstein's special relativity 1905.
Got it.
General relativity around 1914.
So it's a period of intense activity, as you can see. Lots happening. Lots.
And this was also the period through the first, between the first and second, and through the Second World Wars.
Right.
Okay, so it was all the excitement happening at that time in physics. Okay. Anyway, so this was also being observed, that the nuclei of some atoms spontaneously radiate, and this radioactivity was being studied. So you could have positive particles coming, negative, neutral particles. Yeah. So slowly that picture was emerging. Initially, people thought maybe this decays, these are called decays, like when one nuclei changes to another nuclei. The reason that happens is just energetics. All systems try to move to lower energies, because low energy is always, like you keep a ball up, potential energy, it will roll down and try to lower its energy. So nuclei are trying to do that, and that is why they become unstable. And this process is called a decay, when a nucleus converts itself into another nucleus by emitting some particles. Initially, people didn't understand where this was happening, but over the years, and maybe towards, I would say, through the 30s, when ideas of these strong interactions were put in place strongly, at that time, people also started understanding that there's another kind of interaction inside the nucleus, which is responsible for these decays. Okay. It's not strong interaction, but it's a qualitatively different thing, in the sense that, how do you know this? You know this because if things happen through strong interaction, because that interaction is very strong, things happen very fast. If the nucleus were to decay because of strong interactions, it would have decayed much, much faster. But people were measuring the time in the labs.
So Sridhar, this idea of Heisenberg's, how did it come? I mean, was he guided by these observations, or it came out of pure thought somehow?
Not pure thought. I mean, so this observation...
so this was decay, of course.
Right? No, but the strong interaction... Yeah, those came from observations also, and the fact that it was becoming obvious to people that there was a strong interaction.
Right. So unlike
Heisenberg did a little more, which I'll come to.
Right. No, but just going back to this previous, unlike Dirac's situation, this was an interplay in the other direction.
Interplay between theory and experiment.
Yeah, this is in the other direction, experiment leading.
Yes. So a new kind of interaction which was proposed was this weak interaction. And then people started studying systematically many of these decays. And there they found that another new strange phenomenon happening. And that is that when these nuclei decay, somehow they found that energy was not being conserved.
Wow.
Okay. And it's not in this cheating ways. In the reaction, you just have, for example, one nucleus decaying into another nucleus. The process, it emits either an electron or a positron, depending on the charge. Then they found that if you measure the difference in the masses of this nuclei and this energy of the electron, then it should all add up. But that bookkeeping again was not going through. So various proposals came at that time. People said, oh, these are such fundamental processes. Maybe energy conservation is no longer valid. This, that. But at that time, again, this guy Pauli proposed that maybe there is a new particle that is being emitted along with the electron.
Wow.
And he's called that particle a neutrino. Because it's like a neutron, it's a neutral particle. And it's a ino, it's a tiny neutral particle. So Italian for small. So he called it a neutrino. Again. And so he said that not just the electron, but there's another particle being emitted. And of course, that carries away the energy. So energy is all balanced. But the question is immediately, why are we not seeing this particle? So he said, first of all, it doesn't have a charge. And so you don't see it. Then what kind of interaction does this particle have? So this neutrino is the only beast, I don't mean biology again, which has only weak interactions.
Right.
Now, weak interactions, by their very name, they are weak. They are about 1,000 times weaker than electromagnetic interactions. So they're very weak interactions. So a neutrino has very feeble interactions with any other particle. So actually, a neutrino can just go through tons and tons. It can actually tunnel through the earth, without getting absorbed in.
Wow.
So he proposed that this kind of a particle exists, and so one more complication in the picture, two more. We have now brought in weak interactions. We have brought in a neutrino.
So so there's of course a neutrino, this is a little segue, perhaps for a break from this discussion. There's a neutrino observatory coming up.
Coming up, I don't know.
Or whatever. There's a proposed neutrino
observatory. But
right?
there are some.
If you're saying that it's going through everything, what is the proposal for? I mean, what are we?
No, so the ways neutrinos are observed is then you look at their interactions. The only thing that you can do is then look for interactions where you produce from this interaction induced by a neutrino, you produce an electron. Then an electron being a charged particle, you can detect that.
Right.
And it's a inferential.
So the idea of the neutrino observatory is to.
There's a lot of different. It was an umbrella thing for a lot of very different studies with neutrinos involving neutrino oscillations and many of
there are many things
we are not going to be able to talk about today.
Of course. No, this is sort of a...
But that's the proposal is still, to some extent alive.
Right.
But it has got significantly delayed, let's say.
Right. Do you know what this is? That
Where
like the sun. In South India, I don't know the exact location.
It's near Madurai.
It's near Madurai. They're planning to build this, again, underground, huge tunnel where they can study these.
Not tunnel, probably just under the.
It's not a tunnel.
No,
it's
just underground. It's just underground because the rocks will take care of all the other particles.
Yeah.
So what you'll then get is only neutrinos going down all the way. Right. And then you can study their interactions. So early
positron is there, neutrino is there.
Yes.
So far.
And two new interactions
have come.
Yes.
Strong, weak.
Now, people are not going to be satisfied just saying there is strong interaction. They want to understand what is strong interaction. Okay. And around this time, I should take a slight detour and say that, spurred by the success of Dirac's original idea, people went on to, so I have to qualify this by saying what Dirac did is called relativistic quantum mechanics. But what people wanted to do was a quantum field theory. There's a technical difference between these two things. So let's say relativistic quantum mechanics is like a live-in relationship between relativity and quantum mechanics. But quantum field theory is a full-fledged marriage, right? Okay, so when you do the full-fledged marriage, as you know, then there are complications. And in this full-fledged marriage of relativity and quantum mechanics, they discovered some very serious problems, because they found that the first calculations that they could do with it worked well. But when they started doing somewhat more complicated calculations, the next level calculations in that, it just started giving them very serious problems. Okay? Which means what? It means that they would calculate something. The first term is a decent, well-behaved term, some number. But the second term, which they expected it to be much smaller, would become infinite. Okay. So they were getting infinities all over the place. These infinities did not make sense. And through the war, some young people now got into this work. And in fact, these two young people were both Americans, both from New York, both from the same school. They went to the same school, high school together. And Richard Feynman and Julian Schwinger. And they both independently came upon this. And eventually, through a whole process of what is called renormalization, they managed to get rid of these. Renormalization is a mathematical way of handling these infinities. They said that the way the original quantum field theory was defined was in some naive way, but if you do it in a more correct way, then you can get rid of these infinities. Okay. So that was a huge success. And actually, a Japanese physicist called Tomonaga also did this, and they shared the Nobel Prize for this work, the renormalization. And they set in place the first quantum field theory we know, which is quantum electrodynamics. So what Maxwell had done, unifying electricity and magnetism, they did the full quantum version of it. Now, what happens when you do the full quantum version is that the waves that Maxwell was talking about, electromagnetic waves, they get replaced by quantized particles, which are called photons. Now, photons are now commonplace. Everyone knows the word. But that's how they come about. You know, they come about in a relativistic quantum field theory. And this photons, now if you think of how two electrons interact with each other, what happens is electron is here, electron is here. Classically, we'll say these two electrons are both negatively charged and they repel each other. But in quantum field theory, what you say is that this repulsion is because they exchange a photon. And this is effect of this photon that is giving us this picture of repulsion between, or the force between these two electrons is mediated by this photon.
Have you heard of these so-called Feynman diagrams? No. So, I mean, we don't need to go into that. We don't need to go into that. But in case you have heard of it, this picture that he was drawing.
I was drawing.
That is exactly what he was drawing. Yeah, okay. But
so these basically now there are in quantum field theory these couriers, these particles which convey information from one charged particle to another. And in this case of quantum electrodynamics, it's the photons. Okay. So all well, and now this theory is finite, it makes sense, people could calculate things very, very precisely. In fact, quantum electrodynamics is the most precisely tested theory that we have till date, in not just in particle physics, but in all of science.
Yes.
There has been nothing that has been done to that level of precision. Okay. Once you do something like this, the problem is someone says, but what about that? So they have done it for electromagnetism. But now Heisenberg has proposed that there is something called strong interaction between protons and neutrons. So another Japanese physicist called Hideki Yukawa said, just like electrons interact with each other by exchanging photons, and that's what gives you quantum electrodynamics. Maybe protons and neutrons interact with each other by exchanging some particles, like the photons. Okay. But again, in electrons case, there was only negatively charged particles. Here there is proton and there is a neutral particle. So it could be an interaction between a proton and a proton. And then you have to exchange a neutral particle because this is positive, this part. Or it could be a proton and a neutron, then you have to exchange a positively charged particle, or neutron and proton, then it will be a negatively charged particle. So there are all these three particles that are possible. So Yukawa proposed that all these three particles may be the same kind of particle, just plus, minus, and zero charge. And he proposed that there are these particles which, exactly like the photon mediates electromagnetic interaction, these particles mediate nuclear interaction, strong nuclear interactions. And he called them, he or whoever called them pions. Okay. So pi mesons they were called originally, but then they became pions. Okay. Now, again, one more complication. Now, one more particle has come out. The question is, are there pions? If there are pions, can we see them? And as I said, in those days, they were doing cosmic rays experiments. So, cosmic rays are radiation that comes from some outer space, deep inside some galaxies, stars, something produces very high energy radiation. That radiation comes into your Earth's atmosphere. It interacts with the particles in your Earth's atmosphere and it showers. Right. And you sit with your detector on the surface of the Earth and literally wait for the heavens to shower. Upar wala deta hai to chhapar phad ke deta hai. So that kind of philosophy. And so people started doing these kind of cosmic ray experiments to look for these pions. And an interesting side story here is there was this person who was Jagdish Chandra Bose's nephew called D.N. Bose, and he was the director of the Bose Institute, his uncle's institute in Calcutta, and he was a high energy physicist. He had come with training in all these kind of cosmic ray detection from Cambridge. And when he came, he took on a student called Bibha Chowdhuri, and she was a young student, and he just sent her off to do these experiments in Darjeeling because you need to go to an altitude to do these experiments. And she did these experiments and they actually discovered the pion in these experiments. Yes.
Yeah. Have you heard of Bibha Chowdhuri?
Rings a bell, but not really.
Yeah, this is a very interesting case because, there was a very fundamental experiment being done.
And they published
India.
These papers.
Yeah.
Okay. There were problems, partly because I think they were too scared to stick their necks out. The professor should have done that. Right. He should have had the courage to say, yes, we have discovered something. He was partly not ready to do that, I think. But the other practical problem was these were actually being exposed on photographic emulsion. And this was in 1941, so it was at the peak of the war. So they were not getting emulsion, photographic emulsion. So what they had to do was work with what is called half-tone emulsion. What the grainy, in the old newspapers you used to see these grainy pictures, those are half-tone. So the resolution that they had and the statements they could make about the results was not good enough because of this. Okay. But they published their papers without making very strong claims. So in fact, the person who discovered it later did these experiments just after the war. Of course, he had access to the proper material and he got the Nobel Prize for discovering the pion, Powell. Okay. Yeah. So that was a huge missed opportunity.
It's time to colonize, guys. I'm telling you, science is about colonizing.
Well, science is not about colonization because they had access to the fact, the recognition, and the prize.
Yeah, it plays out in
very interesting way. But this particular incident is also very interesting.
Eventually, she came to TIFR and then went to physical research laboratory in Ahmedabad, where she was working, and sadly died in a car accident, I believe. Quite a sad story. I mean, someone who deserved huge, and it would have been such a brilliant thing for India to, at that time, get that kind of attention, and
for a
woman scientist to get that kind of attention. And sadly, even her story has not been talked about for all these years. It's only very recently, the last 10 years or so, 15 years, people have,
Let's make a movie and Akshay Kumar will play her. That's the solution.
Yeah, it's one of the sort of lost and forgotten heroes of Indian science and some. I mean, not entirely forgotten, of course, but could have been much more indeed, right?
Sorry, now we have pions.
Yes.
Then if pions are there, then anti-pions have to be there or something.
So actually the pion plus and pion minus are both there.
Okay.
Right.
So and the pi naught is its own antiparticle. So wahan to theek hai, but pions are there. Okay. Also pion. Okay, there's a technicality there. I don't want to get into. Pions or bosons. And so.
I mean, the other I was just going to bring this up actually, because we also talked about Bose.
Yeah.
I mean, there's also the connection of
we talked
the
about
Bose of the Bose Institute.
So we talked about J.C. Bose, but there was also Satyendranath Bose. Yeah, might as well mention it at this point that there was also other theoretical work going on, and particularly in this interaction between quantum mechanics and what was statistical mechanics. How do collections of particles behave? Earlier we were talking of collection of classical particles, but now we ask the question in terms of quantum particles. And these investigations actually allowed people to understand that there are fundamentally 2 kinds of particles, 10 kinds of binary mein 10. Okay. 2 kinds of particles in this world. One, which are called fermions, named after Enrico Fermi, the Italian physicist. One named after our own Satyendranath Bose, which are called bosons.
Wow.
Now, in quantum mechanics, all these particles, electrons, protons, etc., other than the mass and charge and properties that they also have a property called spin. And spin, naively, one can think of as an electron spinning around its axis. But it's not quite that. It's some mathematical property of it. But it has a spin. So you have something like so if you think of a normal object spinning, you can think of its axis pointing up or its axis pointing down. So this spin is a mathematical thing which is which takes 2 values. So so you talk of the electron with a spin up and the electron with a spin down. Now the thing is, the electron has 2 such values. But if you can have more complicated objects, whether you have more components or no components. So you can have spinless particles, you can have particles with spin half. This half has 2, and then spin 1 particles which have 3, and so on. What these people realized is that particles which have spin half or spin 3 halves or spin 5, like integer spin particles, are half integer spin particles are fermions, are different from particles which have integer spin, which are bosons. Okay. And the main difference is that fermions are such that if you have a electron here, you cannot also have another electron in the same place. So fermions have the property that we know normal matter to have, that normal matter has this materiality associated with it. Materiality is what gives it this thing that it does not allow anything else to come.
You must have from school remember Pauli's exclusion principle. Pauli, so this is where 2 electrons cannot sit in the same orbit.
I also don't remember it. We didn't go to such fancy schools, I think.
Or 12th standard it appears. Pauli's exclusion.
Maybe, but I don't remember.
12th standard, I don't think.
I mean, it's very intuitive. The 2 electrons can't be at the same place.
Right.
I don't know why Pauli had to say this. I could have told you this. Just ask me.
Yes, the reason why it is not intuitive is because bosons don't behave.
Exactly.
Okay. So see, now the thing is we have pushed. So electrons are like bits of matter. All these fermions behave like matter. So the classical distinction between matter and energy now translates into the distinction between fermions and bosons. So fermions behave like matter, so they have materiality, so they don't allow anyone to occupy the same place. It's like a virar fast. Ye mera jagah hai. But bosons can all converge and fall into, condense and go into the same point. Okay, so there is no exclusion principle operating for bosons. Okay, and that is because bosons are strictly not. I mean, we are treating them like particles, but they're actually manifestations of energy.
The
And
interactions.
the interaction. So photons are bosons, to give you an example.
Understood.
Okay.
Understood.
Then there is this very interesting properties of bosons called boson condensation.
You've probably heard of the famous boson,
Huh?
Higgs
the
boson.
Higgs boson.
Yes.
Right.
So the Higgs
Many
boson
people
is
have
an
heard of the
example
Higgs
of
boson.
boson, but
That's
there are
an-
several other bosons.
Yeah. Do you know there's a layer of bosons in the sky?
There's a layer of bosons.
Yeah,
in
it's
this.
called the boson layer. Thanks so much. Sorry, friends. Okay, sorry. Okay, so bosons are there, pions are there, fermions are there, neutrinos are there, positrons are there.
Right.
Lots of them are
No,
here
so
now.
No, but
fermions
he's
and
taken-
bosons are various
Exactly.
ways of classifying
Ah,
all
got it.
these.
So he's
particles.
taken all these things of electrons and put them into two buckets now.
Got
Right?
it.
There are some particles which have fallen into the bucket of fermions. There are others like photons which have fallen into the bucket of bosons.
Got it.
Right? So
So that was essentially the picture. And people, till now, I've been telling you a story where, like he said, theory leads experiment. That you expected something, Yukawa did the theory, pions came out. Dirac did the theory, antiparticles came out, and so on. Right? Or Pauli saw, but he essentially proposed that there was a reason why neutrinos had to be brought in. So
Right.
that also had a proper theoretical basis. But in the same experiments that they found pions, like, when sometimes it rains, particles, it also pours. Instead of just pions, they also found another particle in it. And for a while, they thought it was the same particle. And then after doing things more carefully, in fact, the resolution in the Bibha Chowdhuri experiment did not allow them to distinguish between the pion and the muon. But then Powell could actually pick out the pion correctly. I mean, so for good reasons, he got the Nobel Prize, one should not be unfair to him. But he also saw this other thing, which was the muon track. And this muon is a particle which has no business to be there. There's no theoretical reason why it should be there. In fact, one of the guys who was part of the Manhattan Project, Stuart Raby, when he got news of the fact that this muon was discovered,
who ordered
he
this?
said, "Who ordered this?" So, and the muon is a strange guy. It's just like an electron, but 200 times heavier than the electron, and otherwise has no reason to exist. Okay, and that started off a very strange phase in particle physics from the late 40s going all the way to 1960, throughout the 50s, because people were doing more and more of these cosmic ray experiments. They were detecting things, and it was a time of, best time to be as an experimental particle physicist, because every day you were discovering new particles, and you could write hundreds of papers.
Yeah. How many did they find?
So that is a joke. That is a joke. By the late 1950s, they had seen 100 such particles.
Oh my God.
And they came back to chemistry, because they started with the arrogance that chemistry has 100 elements, we have only 3 particles.
Right.
And by 1960, the story is that you have now 100 particles again.
I think, in fact, Dirac, after his positron prediction and the discovery in experiment, famously remarked that now the rest is chemistry, right? Suggesting that we have done our bit at this layer.
Got it.
Now everything can be dealt with. But it turned out that there was a zoo coming out at this layer also.
So a lot of people have been attributed with this. Now the rest is chemistry.
Now the rest, I don't know. Perhaps it's,
And it's actually probably true that many people actually said
right.
this.
That's probably true. Yeah.
And many physicists, partly because physicists are arrogant, and secondly because they keep repeating the same old jokes. So
That's true.
Great.
But 100 particles by the end of 60s. Basically, no one has a understanding of what it is. And the interesting thing, though, is again, this is where you need to pay attention. So when things become very complicated and messy, you need to sit like Mendeleev and pay attention to the phenomena. Then they tell you some story, and that is a very, very important part of science. Again, it's not about abstract thinking, and not just about. It is also about actually sitting with data, trying to understand what the hell is it. And that was needed at that time. One thing that people noticed is that there is most of the particles, or almost all of them, that except for the muon and so, that they had discovered were particles which had strong interactions. Okay, the electron, I told you, did I tell you that electron does not have strong interactions?
Okay, now I know.
No, it would have been obvious also if you had been paying attention. No, because proton neutron has strong interactions. Electron had strong interactions. It would have been pulled there.
Yeah.
It's sitting outside. It does not have. So the muon also does not have. So those particles which don't have strong interactions, these are just words. They are called leptons. And those particles which have strong interactions are called hadrons. So hadrons and leptons, these are two ways of classifying.
And there's no large lepton collider?
Yes, things are being planned right now. There was a LEP collider earlier in CERN, which was not such a large collider. It was large in terms of dimensions. It is in the same ring. But you cannot accelerate electrons to the same energy as protons because of something called synchrotron radiation. So in the same collider, they could get the electron to go to only about 100 GeV, whereas this is much, much higher in energy. So,
got it. Coming back to leptons and hadrons.
Yeah, so what they observed was the large number of these were hadrons. And so some systematics of hadrons needs to be understood. So, and that job eventually fell on Murray Gell-Mann, who was a physicist from Caltech, who won the Nobel Prize for this work, in fact. So Gell-Mann started looking at this details of this data very critically. There's some story which connects up with spin. Do you want me to tell you that? It's a little technical.
Let's go through the
story. Yeah. So anyway, so Gell-Mann actually realized that you need to. Okay, let me say this much at least. I told you about spin. Okay, so spin comes out of some kind. I told you it's a mathematical concept. It comes out of some kind of mathematics which is called group theory. But it's a very simple kind of group that a mathematical group that is being applied in the case of spin. So Gell-Mann realized that you need something bigger to understand the complexity of this, a bigger mathematical group. And there's a story of how he spent a whole year in Paris struggling to work out what this bigger mathematical group could be. And he could not figure it out. And then he went back to the US after his sabbatical and then just spoke to a colleague who was in the maths department. And that guy said, "You're wasting your time. All this has been done in maths, many years ago." And there's a guy called Cartan who has classified all these mathematical groups. So all that Gell-Mann had to do then was to go and look up Cartan's book and figure out which. So there are these group theory, there are these diagrams. But, he figured out which group works for him and actually used that to understand that these hadrons, the 100 hadrons that you have, can be all understood as coming out of this. So group theory is about mathematical symmetries. So basically, it is allowing you to deduce that there is a symmetry principle at work. And more importantly, the basic diagram that is there in this particular group you were studying, no particle that was observed fitted that basic diagram. And then he realized that this basic diagram is what gives the combinations of this basic diagram is what gives all the other particles. And so he said that these basic diagrams should be attributed to some fundamental particles, and he gave a new name to these particles. He called them quarks. Okay, so at Gell-Mann's time, in the first way he did it, there were 3 quarks, and then eventually, as things went along, more particles were discovered, but they all fitted into the scheme, and more leptons were also discovered. And now we have the standard model where we have 6 leptons and 6 quarks. The 6 leptons, I'll just tell you the names. There's an electron and its neutrino. But the muon also has its own neutrino. It's called the muon neutrino. And then there's a third lepton called the tau, and it also has its own neutrino. So these 6 particles. And on the other side, you have 6 quarks. And this quark is already a funny name, which Gell-Mann took out of a novel by James Joyce called Finnegan's Wake. But these quarks have very quirky names. So the first 2 are called up and down. The second, third and fourth are called strange and charm. And the last 2 are called top and bottom. So now you have 6 quarks and 6 leptons. And these are all the matter particles that we have in the standard. This is what is called the standard model of physics. So before I go further, I'll say...
Where are the other 100 particles?
So
the combination of this.
The 100 particles are all combinations of the quarks. Of these 100 and more are combinations of these quarks. Okay. So you take up quark and you take 2 up quarks and a down quark, you get a proton. You take 1 up quark and 2 down quarks, you get a neutron, and so on. And that combinations are done through using this mathematical group theory. And you can fit all of them and you can explain their... So this way we have all matter is made up of 6 leptons and 6 quarks. Okay. And there is a fundamental theorem which says that if you had 6 leptons, you have to have 6 quarks. Otherwise, your quantum field theory goes wrong. Okay, if you now... Also, these come in pairs, like fast bowlers. Okay, so you could have, 20 years later, discover the 7th and 8th lepton, which is fine. But then you should have the 7th and 8th quark. Otherwise, your theory goes haywire.
Got it.
Okay. So to give you how deeply one believes this mathematical principle, 6 leptons were already discovered. 5 quarks were discovered. The 6th quark was not yet discovered. This talking of 1990s, the situation. And there was a big experiment like the one in CERN now. There was an experiment in Chicago in Fermi Lab. It's called the Tevatron. In that experiment, they discovered the 6th quark, which is called the top quark. And it was taking more time to discover it because as these quarks are heavier, and this top quark is really heavy. So it requires more energy to go and explore it. And so it took that much more time. But no theorist was really, no experimentalist also ever doubted the fact that the top quark would be found.
Wow.
Because the faith in that theorem, which tells you that there should be equal number of these two, was so strong, because that was crucial to the structure of the whole theory, and that much faith was there in that theory. Okay. So other than the 6 quarks and 6 leptons which make up all the matter, then there is energy, the interactions. As I said, photons also take care of electromagnetism, and strong interactions, we talked of pions, but pions were the guys who were exchanging things between protons and neutrons. But now Gell-Mann had taken us to another level in strong interactions. He's not talking of protons and neutrons, but he's talking of quarks. So pions are themselves made up of quarks. Okay. So what is it that quarks exchange between each other? What is the real strong interaction? Because that is a kind of residual strong interaction that Yukawa was talking about. So Yukawa pion has itself a quark structure, and these protons and neutrons are made of quarks. So what is that thing now? If I have to talk about two quarks interacting. But
Money.
no, they interact with a set of particles called gluons.
Okay.
Glue. So
Gluon.
Okay. And similarly, weak interactions are mediated by not one but three kinds of particles, and because they are charged particles, so plus, minus, and neutral particles. So with this set of particles which mediate the interactions, like the photon, the 12 matter particles, the story is kind of complete, except for two things. One is I didn't talk about gravitation. It's the fourth
I
interaction.
was just going to ask you this.
Okay. We believe that gravitation is mediated in the same way by particles called gravitons. Okay. We are not seen. We are nowhere close to seeing it. We don't even know whether gravitons exist in the same way, whether this quantum field theory, which worked very well for these three interactions, whether it works for gravity or not, that we don't know. The only thing is, as I told you, let us go back to the magnitude of these interactions. I said that if you say the strong interaction has the strength 1 in some units, let's say 1, then the electromagnetic interaction is 1 over 100. It's 100 times weaker than the strong interaction. And I told you weak interactions is another, 1 lakh times weaker than the strong interactions. But gravity is in the same scale, 10 raised to minus 39. Okay, so it does not even show up anywhere. So basically, if I get two protons to collide at the Large Hadron Collider, the strongest interaction between them will be the strong interactions, but the protons are also both charged, so they'll also have some electromagnetic interaction, but it's much smaller than the strong interaction. They'll also have a weak interaction because they can both interact through weak interaction, and eventually also have a gravitational interaction because they both have masses. But that gravitational interaction is so tiny that it's never going to show up. Okay. So that is one of the reasons one doesn't talk about the gravitational interaction within the context of the Sand model. But the other important reason is that how to take forward this program of quantum field theory to gravity is still unknown, because gravity is described by an extension of Einstein's theory of relativity, which is general theory of relativity, which involves actually the dynamics of space-time itself. So then you have to start worrying about how do you talk about quantizing such a complicated theory, because it's quantization of at some level of space-time itself. And there has been a lot of progress, and there are a lot of other spin-offs, mathematical spin-offs that have come in the search for such a theory. But I think one can safely say that it's not, the last word on this is not out yet.
Right.
But the fact that gravity does not play a big role in this whole game, it means that you don't see it in experiments. And therefore, if you just look at the standard model, which is just the strong electromagnetic and weak interactions, and compare that with experiments, then
the picture
it's perfect. The agreement between what you see in experiment and what the theory predicts is absolutely good. I mean, there are small glitches here and there, but even those glitches are all getting filled up now. And in fact, the agreement is getting better and better with each passing year.
Friends, with that, we come to the end of the part 2 of this episode of Particle Physics. And maybe there'll be a part 3. Who knows? When it comes, it'll come. Maybe it'll come, maybe it'll not come. And if it comes, maybe you'll be able to watch, maybe not. Who knows? But you've learned so much today. And if you like this, then please write in the comments what you liked. What else would you like to learn about particle physics? What are your questions? Please write those things. Please thank our guest Sridhar for being on this podcast and on this series. You have to love this energy. My energy dipped. I think I'm half your age. I think, and my energy has dipped but he's still ready to shoot part 3 right now. We are dead, so we are not shooting it, but it's coming. Part 3 is coming.
No, and it must be said that part 3, we've ended this discussion of the standard model at a very tantalizing point. There's a very important piece that has to come.
Yeah.
So
Sridhar, guess what is it in the comments? You want to give any hint for them to guess?
No.
No hints. It's difficult. Please guess. Like, share, subscribe, and bring the bell icon, bell the ring icon, whatever that is. And show some love for our guest in the comment section. Thank you. Bye-bye. Bye-bye, everybody. Never see you again.